Hi, good afternoon, everyone, and welcome to our virtual class in Discrete Math. Today's topic would be about Introduction to Sets. We are already on week 2 of our regular trimester 2113. Okay, so let's get started. The objectives that we have for today are the following. First is to be able to define set. Second is to identify the different properties of set. Third would be defining a Venn diagram. And lastly is to be able to solve problems about Venn diagram. First, we have here George Cantor, who developed this theory on sets. So he first encountered sets while working on problems on trigonometric series. Sets are being used in mathematics problems since they were discovered. A set is a well-defined group or collection of objects. So what do we mean by a well-defined group or collection of objects? A well-defined object or group means that it is possible to determine whether an object belongs to a given set. A collection of objects, we have examples here like pack of cards, crowd of people, team in an NBA, basketball, volleyball, team, or even church choir member. Okay. So below, we have here examples of a well-defined set of collection of objects. So people in a class comprising of Mike, Mel, Vance, and Jana. Classes offered by a department, CS101, CS202, CS6202B, or CS6202C, colors of a rainbow, states of matter, cities in metropolitan Manila. And these are examples of well-defined sets. So again, as mentioned, we can determine whether an object belongs to it. Let's say, for example, for people in a class, somebody is looking for Choco. Okay, so you would know that Choco doesn't belong to that class because the class only comprises of Mike, Mel, Vance, and Jana. So that is what's meant that it is possible to determine whether an object belongs to a given set. Cities in metropolitan Manila. So what if someone says Cebu City? So we all know that Cebu City is not part of the cities in metropolitan Manila. A set as well can contain non-related elements, just like what we are seeing right now. The number 8, the letter B, the color blue, and the word mill. Okay, so objects in the collection are called elements of the set. So meaning the items, okay, that you see inside our curly brackets are your elements. Okay, so these are the elements and they are inside your curly brackets. The first property of set is how it is notated. So sets are notated with curly brackets, as you have seen in the previous example. For set, the order does not matter. We often write them in order because it is easier for humans to understand and for uniformity. So we have here an example, 1, 2, 3, 4, 5, which is equivalent to 3, 5, 2, 4, 1. Okay, so just like in my class, whenever I teach this topic to them and then we are having sit work or quizzes or major exam, to always report their final answer, if it contains letters, then they have to arrange it in alphabetical order. If that is with numbers, they have to arrange it in an increasing order. The main purpose for doing such is for the uniformity and of course practicality. Why? So it would be easy to check the paper. Sets do not have duplicate elements. So consider the sets of vowel in the alphabet. It makes no sense to list them as A, E, I, O, 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 U. What we really want is just A, E, I, O, U. So just like the class record of your teacher, so your teacher way back in grade school or high school arrange you depending on the your gender you belong. If, what she will do is she will separate boys from girls, and after that is that she would start arranging the surnames of the student alphabetically. Okay, so one thing that you will observe that there in that list is that it does not list somebody twice. So you would just see the name only once. Why? Because it is not a raffle that follows the saying, the more entries you send, the more chances of winning. So there. Note that a list is like a set, but for a list, the order does matter, and duplicate elements are not allowed. Sets are usually represented by a capital letter, whereas your elements are usually represented by an italic lowercase letter. Easiest way to specify a set is to list all the elements. So you have here an example. It is a capital A, therefore this is set A. And for this example, we don't have letters, so that's why we don't have the italic lowercase letter, but instead we have numbers here. So 1, 2, 3, 4, 5. There are times that it is not feasible to list all the elements, especially if they are too large or it belongs to infinite sets. Okay, so let's say, for example, the answer for that particular question is the natural counting number from 1 to 100 million. So it would be very impractical for you to list all the numbers from 1 to 100 million. So what will we do in order for us to be able to express that value? So the thing that we can do here is that we can use the ellipsis or your three dots, dot, dot, dot. Okay. So we have here an example. Set B is equal to the element 0, 1, 2, 3. And then you have your dot, dot, dot. Meaning this goes until forever. Okay. Until eternity, until infinity. Okay. But the usage of the ellipsis is not always straightforward. Sometimes it can cause confusion, just like what we have here in the example. Consider the set C that comprises the elements 3, 5, 7, then dot, dot, dot. So what if you are asked to determine the second value or the fourth value or the missing value or the value after 7? So what would the answer be? So some of you might answer 9 and perhaps some of you may answer 11. Why? Because the way the set is written is very confusing because we can have more than one answer. Just like what we have here, it could be a 9, it could be 11. If that is a 9, then we are referring to odd integers greater than 2, meaning there are 3, 5, 7, 9, 11, 13, 15, 17, 19, 21. So those are your odd integers. So what about if the next number is 11? So we are referring to the set of all prime numbers greater than 2. So 3, 5, 7, 11. The next number would be 13, 17, 19, 23. So those are examples of your prime numbers. In order for us to avoid this confusion, we can use this set builder notation. When we are expecting an answer equal to 9, then therefore, it should be odd integers. If what we are expecting is an answer equal to 11, then we are referring to prime numbers. So to be able to be clear with our instruction, And how we represent this, again, we can use the set builder. In this way, let's say, for example, we have here D is equal to, or set D consists of all the elements of X such that X is a prime, okay, prime, and it is greater than 2. If we wrote it this way, then the answer should be 11. If we wrote it this way, wherein our X is odd and X is greater than 2, then the answer should be 9. Okay, so again, we have to be very careful on how we use our ellipsis. A set is said to contain the various members or elements that make up the set. If an element A is a member of, okay, is a member of, or an element of a given set S, we use the notation A is an element or a member of set S. Just for this example, 4 is a member of the collections of numbers that you see inside the curly brackets. Is it true that 4 is a member of this? Yes, because we found 4 in our collection of numbers. If an element is not a member of, okay, not a member of, or not an element of a set S, we use this notation. So you can notice here that it's like a letter A, but this time it has a diagonal line for the representation of not. Okay. So in here, 7 is not an element of 1, 2, 3, 4, which is true because you did not find 7 in the collection of these elements. And then as well, this name is not an element of our collection of numbers. So definitely this is not an element. And the answer should be yes. It's not an element of. Okay, so again, without the diagonal, is a member of or an element of. With the diagonal, not a member of or not an element of. Okay. If X is an element of the set A, we write this as X is an element of A. This is your set and this is your element, which is in lowercase. If it is not an element of, again, the symbol would be this one. Let's see these examples here. We have set A and the following elements are 3, 17, and 2. Then we can say that 3 is an element of set A. Why? Because we have 3 in the collection of numbers that we have. Is 17 an element of A? Yes, because we have 17 in our collection of numbers. The same way goes with number 2. 2 is an element of A because we found 2 in our collection. But 5 is not an element of A because we don't have a number 5 in our collection. Another example here is if set A contains the element of all X such that X is a prime number, then 5 is an element of A and 6 is not an element of A. So how will we know? So we have to list the values first. So examples of prime number greater, okay, so 2, 3, 5, 7, 11, and then, okay. So is 5 an element of our collection of prime numbers? Yes. Is 6 an element is not an element of our set A? Yes, because it does not contain 6 here. So therefore, 6 is not an element of A. So I have already introduced to you the set builder notation. So let's talk about it. Let's talk about it more. So set builder is a method that lists the rules that determine whether an object is an element of the set rather than the actual elements. The set builder notation has the general format. You have here your curly brackets. Do not forget that. You have your variable. You have the vertical line and your descriptive statement. The vertical bar, this one, is always read as such that. Set builder notation is frequently used when the roster method is either inappropriate or inadequate. So variables can be X, Y, Z, or any letters from the alphabet. Okay. In other books, you would not see a vertical bar, but instead you would see colon. Okay, but that is still correct. So let's say, for example, you're asked to express the statement all cities in the Philippines in a set builder notation. So how will you represent that? Okay, so this is how we represent this sentence into a set builder notation. Okay, so you have your letter A, your equal sign, your bracket, your variable, your vertical bar, and then you have your descriptive statement. And then lastly, your curly brackets. So how are we going to read it? So one way of reading this is A is the set of all X. Okay, such that, again, such that X is a city in the Philippines. Again, A is the set of all elements such that X is a city in the Philippines. Okay, so we have here examples. We have here X such that X is less than 6 and X is a counting number. So it is the set in the set builder notation, right? So what if you are asked to express this X such that X less than 6 and X is a counting number into a roster form? So it is just the set of all counting numbers less than 6. So that this expression, this statement is equal to 1, 2, 3, 4, 5. So you would notice that these numbers we have here are all numbers less than 6. Okay. So next, what if you are asked to express this set builder notation into a roster method? Okay. So X such that X is a fraction whose numerator is 1 and whose denominator is a counting number. So let us start our list with 1 over 1, 1 over 2. Remember, a fraction contains a numerator and a denominator. And that is indicated in the condition that our numerator will be equal to 1. And our denominator should be a counting number. So you would notice here that all the number that you see in the numerator is 1. And at the denominator, these are counting number. So this is the equivalent roster form of this expression expressed in set builder notation. Okay, so the set builder notation will become much more concise and precise as more information is introduced, just like in here. So there is no confusion on what we are going to do. Okay, so I kept mentioning about the roster method. So the roster method of specifying a set consists of surrounding the collection of elements with brackets or braces. So for example, the set of counting numbers from 1 to 5 can be written like this. So you have your curly brackets and then your elements are inside the curly brackets. Okay, so a variation of the simple roster method uses the ellipsis when the pattern is obvious and it doesn't make any confusion. and the set is large. So this is the only time that you will be allowed to make use of the ellipsis. So we have here 1357 up to 9007. So this is the set of odd counting numbers less than or equal to 9007. Okay, so you have here the ellipsis in the middle. So what does it mean? So we are just omitting all the numbers between 7 and 9007. But these numbers that we omitted are understood to be odd counting numbers. So for practicality, we omitted all these values because if we're going to write all the counting numbers from 1 to 9007, that would be very lengthy. It would take some time for you to finish. Okay. And here is another variation. You saw the ellipsis on the right side of the last number. So meaning this is the set of all counting numbers to infinity. So here are examples of sets in mathematics that makes use of ellipsis. Capital N is for your natural counting numbers. So when we count, we start with 1. So how many dogs you have? Of course, you start with 1, 2, 3. If you have more than one dog, okay? Up to the positive infinity. What about capital letter Z? Your letter C is the set of all integers from negative infinity to positive infinity. What about Z negative? So it is the set of negative integers. So that is from negative infinity. From negative 1 to negative infinity. What about W? So your W is your whole number. But this time, it starts with 0. So that is the difference between a whole number and a natural number. Okay, in the whole number, you begin with 0. For natural counting number, you begin with 1. A set is a subset of the set B if every element of A is an element of B. It is denoted by this symbol. Okay, so it's like a letter C with a horizontal line. That is for a subset. So the definition itself is quite questionable because some of you might not be able to get it in the first reading. But to make it easier for all of us to understand, so let us see an example here about notation, of course. If A is a subset of B, we write it this way. A, B, your sets, and the symbol for the subset. If that is a proper subset, okay, proper subset, you would notice that the horizontal line was omitted already for the proper subset. And then for if A is not a proper subset of B, so again, you have here the word not. So we're just negating the proper subset. Okay, just like the not element of, not a member of. You will see that there is a diagonal line. So let us consider this example for subset. Set A contains the elements 1, 2, 3, while set B contains the elements 1, 2, 3, 4, 5, 6. We can say that A is a subset of B because each element of A, example is 1, can be found in set B. In A, which is equal to 2, can be found in set B. Number 3, in A, can be found also in set B. So if that is the case, we can say that A is a subset of B. Okay, so we can also write it this way. Okay, so if you are going to refer to the above given, set A contains the following elements, 1, 2, 3. So this is your set A, okay? Is a subset of set B. Okay, so there. 1, 2, 3, 4, 5, 6 are the elements of set B. In here, we have another example, of course. The set A is not a subset of set B. Why? Because although you have seen 5 from A to B, and then 7 from A, and then you also have 7 in B, but our number 3 here is not an element of B. So therefore, we can say that A is not a subset of B. Here, you have to remember this because we will be acquainted with this later on. There would be examples and concepts wherein this one will be utilized. The empty set is a subset of every set. Okay. So the set A that contains 1, 2, 3, 4, 5, which is in roster form, and B, which is in the set builder notation. If I'm going to write this is in its equivalent roster form, that would be equal to 1, 2, 3, 4, 5 also. Okay, for set B. So what did you notice? The elements in A is found in set B. The elements in B is found in set A. So what can be said about that? A is a subset of B, and B is also a subset of A. Okay, because every element of B is an element of A. The same way it goes with A, every element of A is an element of B. We have now the proper subset. If A is a subset of B and B contains elements which are not in A, then A is a proper subset of B. A set A is said to be a proper subset of B. You would see here the representation again for proper subset. And these are the two conditions that we have to check before we can say that given sets are a proper subset of each other. Okay. So here, B is called a superset of A. So let's see some examples here. Consider the sets A that contains the elements 5, 6, 7, and set B contains the elements 5, 6, 7, 8. Okay, so you would see 5 from A to B. The same way goes with 6 and 7. So we can say that A is a proper subset, a subset of B. And since you would also notice that 8, we have an extra number here, which is 8 in set B. So let us read this again. B contains elements which are not in A. So we have an element in B which is not in element A, right? Right? You did not see an 8 here. So therefore 8 in B is not an element of A. So we can say that A is not equal to B. Notice that we have met the two conditions for a proper subset. Here, A is a subset of B and A is not equal to B. So we can say here that A is a proper subset of B. And there is one thing that you have to note of. The superset. What about a superset? In here, B is called a superset. If you're going to determine the cardinality or the number of elements we have in this set, this would be equal to 3. If you are going to determine the cardinality of the elements in set P, that would be equal to 4. Let us read the remarks. Proper subsets have at least one element less than its superset. So 3 is less than 4. Okay, so remember that our B here is our superset. So there is no set which is a proper subset of itself. So a given set will be a subset of itself because it will contain the same element. And then the third remark, the empty set is a proper subset of every set except the empty set itself. So later on, you will be having examples of this. There are two improper subsets of any given set, the empty set and the set itself. With this definition, here are the consequences of this. The first would be every set is a subset of itself. Okay, so you would see yourself, right? So if you look into a mirror, you would see yourself. You would not see a different image aside from yourself, right? So let's say, for example, you have 2 ears, of course, up till now. And then when you look at the mirror, you would notice, oh my God, where is the other ear in the image? So that can never happen. Okay, so if we have 2 ears, and then when you look into the mirror, there should always be 2 ears as well. 2 eyes, 1 nose, 1 mouth, right? So it is a subset of itself. An empty set is always a subset of every set. So meaning it is always there. Okay. An empty set is always a subset of every set. The empty set is represented by this symbol. Okay. Empty set. Sometimes it can be represented by the 2 curly brackets. But this time there is nothing, okay, inside the curly brackets. That's why it is called an empty set. There's nothing here. But in these 2 examples, these are not empty sets. Why? Because it contains one element inside the curly brackets. So once there is something here, it is no longer not empty. Okay? Sorry, it is no longer empty. The empty set has only one subset, which is itself. Okay, just like this one. The empty set is always a subset of every set. Here are the different types of sets: empty, finite, infinite, equal, and power sets. The set with no elements is called the empty set, or the null set, or the void set. Okay, so these are the other terms used to describe or used to be called for an empty set, void or null. And it is designated by these symbols. And then this one, curly bracket. Examples of empty set. The set of all pencils in your briefcase might indeed be the empty set. So if you have a briefcase and there's no pencil in it, so it's an empty set. Sir, what if I don't have a briefcase? so that's a different thing. The set of even prime numbers greater than 2 is the empty set. Why? Because there's no other even number that is considered to be a prime number except number 2. In here, the set x such that x is less than 3 and x is greater than 5 is the empty set. So let us just write this first, the equivalent of x less than 3. So let's say, for example, that is 1 and 2. And what about this? X greater than 5. So 6, 7, 8, 9. So if we have a number 3 here, is 3 greater than 5? No. Is it less than 3? No. What about number 4? Is 4 greater than 5? No. Is it less than 3? No. What about 5? Is 5 less than 3? No. Is it greater than 5? Definitely no. So there is no number that exists that has met this condition. Therefore, it is the empty set. We have here the finite set. When we say finite, it only contains a countable number of elements, which means we can count it. So example would be the number of shoes you have, the number of slippers you have, right? So what else? The number of white t-shirt you have in your closet or in your drawer. So all of that is countable, right? So one obvious example here is the days in a week. Okay, so what are these days in a week? These are Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So we can count them. That's why it is countable. And of course, the opposite of finite, which is infinite, which is something that we cannot count because it has no end. It is the infinite set. Okay, so you have here the set of integers z, our n, our natural numbers, negative integers, z to the negative, and non-negative integers or your whole numbers are examples of infinite sets. Okay, so this is the example that we have discussed earlier. These are your counting numbers to the infinity, to infinity, to infinity, and to infinity. So these are infinite sets. Two sets and A and B are equal if A is a subset of B and B is a subset of A. If two sets A and B are equal, what would be the representation? Of course, the equal sign. If that is equal, then the equal sign. So let's have here an example. A that contains the elements 3, 4, 6, and B contains the elements 6, 3, 4. So A is a subset of B. Okay, so you found all the numbers of the elements of A in set B. The same way with B. All the elements of B is found in A. Therefore, B is a subset of A. If that is the condition, that is an equal set. Okay? The definition of equality of sets shows that the order in which the elements are written does not affect the set. Okay, another example, 1, 2, 3, 4, 5. And then if we express this into its corresponding roster form, so that would still be 1, 2, 3, 4, 5. And they are both subsets of each other. So therefore, we can write it as A is equal to B. Okay, what about for the not equal? So you will have this symbol, okay? So based from the example that we have for the proper subset, it is definitely not equal because the other one contains more elements than the other one. Okay, so in here, set A contains the element 2. B contains the elements 2 and 5. So again, we can say that A is a subset of B, right? But B is not a subset of A. So we cannot say that A is equal to B. It should be that B must be a subset of A before we can say that A is equal to B. And then we have the equivalent. Sets A and B are equivalent, denoted by the tilde symbol if they have the same number of elements. In here, it doesn't matter if the elements inside the curly brackets are the same. what we are just after is the number of elements inside the curly brackets or your, let's count this, 1, 2, 3. And this one is 1, 2, 3 as well. So each of this set contains the same number of elements. So therefore, we can say that A is equivalent to B. Again, the term for that would be determining the number of elements. That is cardinality. Okay, so cardinality. And then we have the power set. The set of all subsets of A is said to be the power set of the set A. So we have here the example. Set A contains the element 3 and 4. So if you are asked what are the subsets of this power set, so we begin again with the concept of the empty set. It was mentioned that for an empty set is a subset of every set. So it's always there, the empty set. And then the first element, we have the second element, and then the combination of the two elements. So how will we know how many subsets are there in a given set? So this is how we determine it. We use the formula 2 raised to the n. Okay, so let us consider this set that contains elements 0 and 1. So what would be the cardinality? The cardinality of this is equal to 2. So our n is equal to 2, and we will substitute 2 here. So that's going to be 2 squared, which is equal to 4. So again, you would see here the empty set as a subset of itself, 0, 1, and then the subset of itself, 0 and 1, or simply A. So what if our n is equal to 3? So that is going to be 2 raised to the third power. So that is going to be 2 times 2 times 2, and that is equal to 8. Okay? So what would be the different subsets of this power set of set B? So it would start with 0, or no 0, but the empty set. Okay, again, the empty set, A, B, C, the combination A, B, AC, and BC, and then the 3. So if we are going to count it, we have 1, 2, 3, 4, 5, 6, 7, and lastly, 8. So these are the power sets of set B. Okay, so you just count or determine the cardinality and then use that as the exponent of our 2 raised to the exponent n, and then simplify. You would be able to determine how many power sets or subsets do we have of a power set. Okay, so here, so 2 to the n again. The empty set contains of course no element, so that is 1. The subset of itself is the empty set itself. If that is 1, so 2, that is 2, that's equal to 4. If that is 3, that's equal to 8. Okay. And next we have the Venn diagram. It is frequently very helpful to depict a set in the abstract as the points inside a circle or any other closed shape. Some others use rectangles, squares, pentagons, hexagon, as long as it is a closed shape figure. So John Venn, who is a British mathematician, used diagrammatic representation as an aid to visualize various relationships between sets and set operation. Actually, Venn diagram is not just used in math, but it is used widely in many other fields like logic, theological ethics, genetics, study of Hamlet, linguistics, reasoning, and many other areas. The first definition for a Venn diagram that we will discuss is the intersection. The intersection of two sets A and B is the set containing those elements which are elements of A, take note of, and elements of B. For intersection, the word that we are going to use to describe it is the word and. And we represent it by this a cave-like symbol. Okay, so we write A intersection B. So this is the symbol for intersection. So if we have here two sets A and B, A is 3, 4, 6, 8, and B is 1, 2, 3, 5, 6, then A intersection B is 3 and 6. So how did we come with this, or how did we arrive with this answer? Intersection is commonly understood by many as the thing that is common between sets. In set A, you have here 3, which is common also or seen in set B. In set A, you have seen 6 here, that is also seen in set B. 4 and 8 are not seen here. The same way goes with 1, 2, and 5, which are not seen in this given set. So in other words, common figures, common name, common, anything that is common to both the sets, then we can write it as their intersection. Speaking of symbols, okay, so we will see, or we will determine here the intersection of these symbols for set A and B. So you would see that this symbol is common to both set A and B. This symbol also is common to both sets A and B. What else? This one, right, is common to A and B. But the other symbols are not common to each other. Therefore, the intersection of A and B are these three symbols that we have here. Okay? And then for this example again. So you would notice that this is common. Okay? There, these four figures or symbols are common to each other. Then therefore, the intersection are these common figures. Why is it equal to B? Sir, why is it equal to B? Because set B contains all these elements that we have in the final answer. So therefore, it can be written as A intersection B is the set B itself. We have here, if A set of prime number, if A is the set of prime numbers and B is the set of even numbers, then A intersection B is equal to 2. How? So let us write again the prime number. So that starts with 2, 3, 5, 7, 11, and then you have your, okay. And then for set of even numbers, so it starts with the 2, 4, 6, say for example, you have 8, 10, up to infinity. Okay. So what is common to both? Obviously, it's the number 2. That's why the intersection of A and B is equal to 2. What about this one? X is greater than 5. So these numbers begins from 6, 7, 8, up to infinity. What about X less than 3? So let's say, for example, you have 1, 2. So is there a common number between the two sets? None. That's why it's an empty set. Okay? What about this one? X less than 4. So what are the numbers less than 4? Which are counting numbers? So 1, 2, 3. And X contains a number greater than 1. So that is 2, 3, 4. Okay? And let's include 5 and the dot, dot, dot. Okay? So there's a curly brackets there, okay? So our answer would be 2 and 3, right? Which are common to both A and B. So if we are going to represent our answer in a roster form, it would be 2 and 3. But if we are going to express this answer in a set builder notation, this is how we write it this way. Okay? So let us check whether this set builder notation equals our roster form. So it says here that our x should be greater than 1. Are these numbers greater than 1? Yes. And x is less than 4. Are these numbers less than 4? Yes. So therefore, this is the equivalent expression of the answer in set builder notation. What about this one? X greater than 4. So we begin writing the number from 5, 6, 7, 8, 9, 10, 11, up to dot, dot, dot. Okay. So we might be corrected here if somebody sees this. Okay, so let me complete that. And then x greater than 7 starts with 8, 9, 10, 11, 12, dot, dot, dot. Okay. So if you would notice, the numbers 8, 9, 10, 11 up to infinity is common to both. So therefore, 8, 9, 10 up to infinity when written would be the intersection of these two sets. That is in roster form. And this one is in set builder. So let's see. Are these numbers we have here 8, 9, 10, 11 to infinity greater than 7? Yes. So therefore, we can express our answer this way instead of writing 8, 9, 10, 11, dot, dot, dot. That's still considered, which is considered correct. And then we have here the Venn diagram, the concept. The second concept is union. Okay, so union is not hard to memorize the symbol because they look alike. It's like a letter U. Okay, for union. A here, our A, which is in blue, and B is represented in red. So the purple colored region illustrates the intersection, meaning what is common to A and what is common to B is in the middle. Okay. But in union, it consists of all the points which are colored red, blue, purple. And the word for that, for union, would be or. For intersection, it's and. Okay. The union of two sets A and B is the set containing those elements which are elements of A or elements of B. Okay, in layman's statement, union would be combining them, but make sure that the elements of the set is just written once. Okay, so in here, you have here A union B. Set A contains 3, 4, 6, and B contains 1, 2, 3, 5, 6. Okay, so you would notice here that we have 2 3s, and then we have 2 6 as well. But again, it should be written only once in our answer. So you combine 1, 2, 3. Then you have your 4, 5, and 6. So you just combine them. Okay. Okay, so we just combine this. Okay, although you have noticed here that these symbols, what else? This one, it should be written just once. Okay, as you can see here. No duplication of elements. The same way goes with these two sets. So you just write it, combine them. Again, it is equal to A. Why? Because the answer is similar to what is contained in set A. Here, if A is the set of prime numbers and B is the set of even numbers, then the union, take note, X is even, so that is our set of even, or X is prime, so that is prime number. We just combine them and then connected with the word or. The same way goes here. X greater than 5, X less than 3, as you can see here, combine them and then connect it with the word or for union. Okay? Here are some algebraic properties that we should observe when simplifying. Okay? Union intersection problems. So in here, the commutative. So A union B is similar to B union A. It doesn't matter how we write it in order. A intersection B is equal to B intersection A as well. That's for the commutative. What about the associative? For the associative, it concerns about groupings. That's why you would see there a grouping symbol, and that's a parenthesis. In the first example that we have here, A and B are grouped together, but in here, B and C are grouped together. So what did you notice? These two are just equal. Okay? So whichever you grouped, the result would be just the same. But in simplifying, you have to make sure that you simplify first the operations inside the parentheses before you proceed with the other operations like PEMDAS, right? Parentheses, exponent, multiplication, division, addition, subtraction. And then we also have here for intersection, okay, grouping symbols. So again, you simplify first what is inside the parentheses, then proceed with the next operation, and then the answer would be just equal. And the third is distributive loss. So in algebra, you have, let's say, for example, y, and then multiply to x plus 3z. Okay, so when we distribute, we multiply y to all the elements inside the parentheses. So that would be xy plus y times 3z. That would be 3y and z. Okay? But in sets, it would be not that as direct as the one that we have in algebra. So observe here that the symbol inside the parentheses, okay, inside would be the one outside. The one outside the parentheses will now be the symbol inside the parentheses. The one inside the parentheses will now be the one outside. The one outside the parentheses will be the one inside the parentheses. Okay, so you have to take note of that. That is how you distribute the symbol. And here are some elementary properties of intersection and union. The union of a given set to nothing is the set itself. The intersection of a given set to nothing is nothing. Okay? There's no common to having nothing and to having some. And then the union of the set itself is the set itself. The intersection of the set itself, of course, that is the set itself.